Welcome to the second part of our two-part lecture series on cryptology. My name is Ron Richter. I'm the program coordinator here at Blue Ridge Community and Technical College, and we're going to finish our discussion on cryptology. So in our last series, we were talked about the differences between a hash and a cipher. So today we're going to take this idea of ciphers a few steps further. So what makes a cipher different from a hash is that a hash is a one-way algorithm. A cipher is a two-way or reversible algorithm. Ciphers come in really two varieties, symmetric and asymmetric. Let's first examine the symmetric. The symmetric encryption algorithm can sometimes be referred to as a private key cipher. Relies on a shared secret key to both encrypt and decrypt files or messages. The key part of that phrase is shared secret key. There's actually two subcategories of symmetric ciphers. The stream type of symmetric cipher. With a stream, the encryption engine replaces or substitutes one character at a time. A good example of a stream encryption algorithm is a substitution cipher or a transposition cipher, where you're substituting one letter for another, or you're transposing one letter in a word for another letter in that same word. The stream cipher is relatively fast when the plain text is relatively short. Compare that with the other category of symmetric encryption algorithm, the block cipher. The block cipher manipulates an entire block of text at one time, either in 8 or 16 byte blocks. So now the encryption engine is acting upon an entire block at a time rather than one character at a time. Relatively speaking, block ciphers are much faster when the plain text is relatively long. In terms of security, a stream cipher is relatively less secure than a block cipher because, again, the encryption engine is doing the same exact thing over and over again, whereas the encryption engine for a block cipher is acting on an entire block at a time, so it never acts the same way twice. The encryption process for a symmetric algorithm, either block or stream, is the same. We can take our unencrypted text or our plain text, which in this case is in the form of a message. We can apply the encryption algorithm along with the specific key, and in this case we're talking about a symmetric encryption process, so this is a shared secret key. The key and the algorithm are combined along with the plain text message to create the ciphertext. Now we have a secure piece of data that can be transmitted. It can be transmitted to a remote user where the ciphertext can be combined with the same key and the same decryption algorithm, decrypting it back into legible text again. So that confidential memo layoffs at the Lakeview store will begin can be sent securely, decrypted, and the original message can be retrieved. Examples of types of symmetric ciphers or private key ciphers, again, are many. Each of these ciphers come from a family of ciphers that have evolved over time, usually because of key strength becoming larger and larger. And again, the larger the key, usually more secure the algorithm is. The Rives family of ciphers, RC2 up through RC5. 2 and 5 being of the block variety, 4 being of the stream variety, evolving to what we use today, the DES, the triple DES, and the AES. Digital encryption standard, triple digital encryption standard, which just performs the same algorithm 3 times, and the advanced encryption standard, which is the encryption standard that the federal government insists that federal agencies use today to protect federal information. Symmetric ciphers provide more protections than hashes, obviously. They do provide that protection of confidentiality because we can use that shared secret key to convert that plain text into ciphertext, and it can be transmitted confidentially. It can prove integrity because without that shared secret key, you can't retrieve the original data from the encrypted data. It gives us the protection of availability because that data can be exchanged freely as long as the key is shared with the intended recipient. It can provide authentication because you can authenticate the recipient is authorized to receive that data because they happen to be in possession of the key. The only protection it cannot provide is the protection of non-repudiation. Whoever has possession of that key has the ability to decrypt it. And they also have the ability to encrypt the message in return to the original sender. But there's no way to authenticate who that actual person is. So there's no protection of non-repudiation. But what's the weakness of that shared private key? The weakness of symmetric encryption is just that. The private key has to be kept private, but it has to be shared. That means that the key either has to be transmitted through snail mail, through electronic means, or hand-delivered from origination to destination. That in itself is a weakness, because at some point in the transportation from origination to destination, the key can always be intercepted. Asymmetric encryption algorithms overcome that weakness. We refer to asymmetric encryption algorithms as public key ciphers because this cipher uses a set of keys, a set of mathematically related public and private key pair rather than a shared secret key to encrypt and then decrypt messages. These keys are generated and mathematically related. They never have to be exchanged. The public key is freely available to everyone and will be published. The private key would only be known to individual to whom it belongs. And the beauty is the key's worth in both directions. You can send a message with a public key, decrypt a message with a private key, and you can send a message with a private key and decrypt a message with a public key. How does this work? The process of asymmetric encryption is pretty simple. We can begin with the same plain text message. Layoffs at the Lakeview store will begin. They can be encrypted using the public key of Alice, the recipient, combined with the encryption algorithm to create the ciphertext. That ciphertext can be securely transmitted to the recipient, in this case Alice. It can be decrypted with Alice's private key, to which only Alice has access to. And the ciphertext can be deciphered into plain text. Various examples of asymmetric encryption we can look at today. Diffie-Hellman is an example of asymmetric encryption. The Diffie-Hellman algorithm is actually the algorithm that many times is used to generate the public and private keys. RSA is another heavily used asymmetric encryption. It stands for the Rivest Secure algorithm. Elliptical curve, ElGamal, DSA are all currently used types of asymmetric encryption, but Diffie-Hellman and RSA being the most prevalent used today. Now it's interesting to note asymmetric encryption is much slower, relatively speaking, than symmetric encryption. For instance, regular old DES is 100 times faster than RSA encryption when performed in software, and actually tens of thousands of times faster when performed in hardware. But asymmetric encryption provides protections that symmetric encryption can't provide. It provides confidentiality, like symmetric encryption. It can provide integrity, like symmetric encryption. It can provide availability, like symmetric encryption. It provides this protection of authentication, like symmetric encryption. And it also provides this idea of non-repudiation. Because a message sent by Alice with her private key, to whom she's the only one who possesses that private key, can only be received by someone possessing her public key. And because she's the only person with access to the private key, provides this idea of non-repudiation. Alice could never deny sending that message because it could only come from Alice. So this idea of asymmetric encryption is the idea behind digital signatures that we use today. Because asymmetric cryptography can be used to provide proofs. We can have proof. Suppose that Anne received an encrypted document that says it came from Bob. Anne can be sure that the encrypted message was not altered by someone else during transmission, but how can she verify the document came only from Bob? Well, if Bob's private key was used to encrypt that message, it could have only come from Bob, because only Bob has possession of that private key. So that is symmetric and asymmetric encryption. I thank you.